Alrighty, chapter 27, number 15. An electron at point A has a speed v0 of 1.41 times 10 to the 6th meters per second. Find the magnitude and direction of the magnetic field that will cause the electron to follow the semicircular path from A to B and the time required for the electron to move from A to B. So, in order to get our electron that's moving this way to start moving in a circle, it has to start feeling some sort of force. That force is caused by a magnetic field. And since we're dealing with a point charge, that force is QV cross B. Cool? So, as we're moving this way, we have our QV, but we're dealing with an electron. So our QV is this way, cross B, and then our thumb is going to be our force. So I'm feeling a force to the right. So that's my thumb. My QV points in the direction of the velocity, but since I have an electron, that's going to be in the opposite direction. And so my middle finger is going to be my magnetic field. So that's going to be pointing into the page. So B has to be into the page. So when we talk about into the page, we use this little X symbol. So you can think of it like shooting arrows. So if you're shooting an arrow into the page, you see the feathers on the end of the arrow. And if you're shooting an arrow out of the page, you see the point. So into the page is feathers. Out of the page is, I like to refer to them as bullets and feathers. So bullets are getting shot in the face, it's coming out. Feathers are shooting away from you. Alright, so anyway, so that's how we figure out the direction. So now, this force from the magnetic field is causing us to move in a circle. So if we look back to last quarter, that's going to be a centripetal acceleration. So we have our QV cross B is going to be equal to mv squared over r. Now, because our V and our B are perpendicular to each other, that's just going to be QVB. So one of our V's cancels out. So I have mv over r equals QB. So B equals mv over QR. So I'm dealing with an electron, so it's like 9 point something something. Let me look it up. It's like 9 something to the negative 31. Mass of an electron, 9.1 times 10 to the minus 31. Kilograms. Our initial velocity is 1.41 times 10 to the 6 meters per second. Our charge, now we're just looking for magnitude of the magnetic field, so I'm just going to plug in the magnitude of the charge. Since we already used the negative sign to figure out the direction. And r is the radius of the circle, so that would only be 5 centimeters. Right. So now if I take this handy dandy calculator that belongs to Michelle Zhang, who still hasn't claimed it despite numerous attempts to reach her. So if you know who that is, tell her I have her stuff. Okay, times 1.41 times 10 to the 6, splat, divided by 1.602 times 10 to the minus 19 times 0.05, splat. So the magnitude of our magnetic field is going to be 1.6 test times 10. Wow, I can't really talk today. To the minus 4 Tesla. Alright. So, for part B, to figure out how long it took, even though we're pushing it into a circle, we're giving it a centripetal acceleration. We're not actually changing the speed of the electron. So we can use good old distance equals velocity times time, because we're going at a constant speed. So our distance here is going to be this circumferential little difference. So the circumference of a circle is 2 pi r. Circumference equals 2 pi r. We're only going half of that, so our distance that we're traveling is pi r. So pi r equals velocity times time. So our time is pi r over v, pi 0.05 meters over our speed, which didn't change. So we have, where's the pi button? There it is. Okay, pi times 0.05 times 1.41 times 10 to the 6. Divided by, hi, I'm not the brightest cookie in the box today. Divided by 1.41 times 10 to the 6. Okay, so that time it takes is 1.11 times 10, so minus 7 seconds. Sweet.